atmospheric science students, this is Dr. Schragi, and we are ready to start learning about writing C programs in this class. C is a computer programming language. It's going to be the language that we're using in this class. I was just talking the other day to a student, and they wanted to know, is C what research tends to be done in meteorology? And the answer is maybe not really. But a lot of computer languages that are similar to C do tend to be the way computers programs are written in atmospheric sciences. And so we kind of had to make a choice as to what to use, and kind of the common denominator seemed to be C. There are other computer languages we could use that you might be somewhat more likely to see that exact language in a job someday. You might see C, but more importantly, you'll be quite likely to see computer programming languages that are quite similar to C. Other languages, it might have been quite different. There's a whole lot of these different computer languages out there. Let's go ahead and start learning about the very basics of how you're going to work with a C program. C programs are files. They're a file that's going to exist at some location on the hard drive of the computer. We're going to be learning all about that this semester as to how we know where they are and what a file even is. But I think at this point in time, you guys all know at least kind of roughly what a file is. We're going to be creating files just like you did like with the web design part of the class, where you were using a tool, an editor, to create files. We're going to continue using the tool VI just because it's a very powerful tool. It's a very old but very powerful way to edit files. And files that are C programs always end in the extension .c. So like if you're going to make a program called test, you would make it test.c if it's a C program. This extension, the part beyond the dot, doesn't actually mean anything in a Unix computer like the computer that we're using in this class, the way it does on like a PC or a Mac. On a PC or a Mac, Word opens files that end in .docx, or Excel opens files that end in XLX or XLSX or whatever the right word, acronym is. .gif files are GIF images, and so on. Unix itself, Linux, does not care what those extensions are. In practice, you'll see that, in theory you could have called this anything. You could have called it test.c, or you could have called it test.myprogram, or whatever. In practice, though, as sort of a security thing, a program that we're going to use in a little bit called the compiler, just for security purposes, it will only even try to put together or compile programs that end in .c. That way, it knows that you know what you're doing. You've correctly identified that these are the C programs in your account, and so on. So if we were going to be making changes to a program called test.c, or just creating a program called test.c, we would open a new blank file by typing vi space test.c to start the process. Now, every C program out there has to start with the same two lines. They are kind of a pain in the butt as lines go. They are pound include, and then in angle brackets, math.h, followed by pound include, and then angle brackets, xtdio.h. What's actually going on here? C is actually a very, very simple language. C is the very, very most primitive tool in your toolbox. Imagine if you were looking in someone's toolbox. If the people in the toolbox have kind of a heavy but flat rock and a bent stick and a few other things, you know what? They can build a house. Okay? They got to use that rock as a hammer, and then they're going to use their stick maybe to hold this and pry on this. That's kind of what C is like. It's a very simple set of tools. That's in contrast to if you open up the drawers at your dentist's office and you look in there and they have all kinds, hundreds of different little tools for scraping and picking and so on. Other languages are more like that. Okay? C is so dumb, C is so basic, it doesn't even know things like plus or minus or multiplication, much less somewhat more complicated mathematical things like sine, cosine, tangent, and so on. Okay. Clearly, almost anything you do with a computer is going to require, any kind of scientific computing is going to require being able to do some math. Okay, so what you do is you include the math libraries. Someone has gone ahead and written, we'll learn that these are functions that give C the ability to do things like add, or subtract, or knows the orders of operations when you have parentheses and things like that. In order to have any kind of math whatsoever in your program, then you have to have included the math libraries. Or the way it actually is written here, that you're including the math headers. That's why it's .h, they're for headers. Similarly, STDIO stands for Standard Input and Output. C is so basic and so simple, it doesn't even have the ability to print something to the screen. It doesn't even have the ability to do something as complicated as ask the user to enter something. You know, like what is the current temperature, and then they type in 32. Okay? Well, clearly any program is going to need that kind of stuff, and somebody created a library of the tools that you'll need, like print and things like that, and they put it in a file called stdio.h, the Standard Input and Output Headers. We'll never ever write a program that doesn't need math and doesn't need standard input and output. So just think of it as every program always has to start with those two lines. Pound include math.h and pound include stdio.h. Then, every program has to have what we call the main function. Main is where the program is going to start. Execution, where is the computer going to start doing the commands that you give it. It's not necessarily at the top of the program, it's going to be wherever you have main. And you can see the syntax here. It's actually main, and then a pair of parentheses, and then a curly brace, followed by some blank lines, and then a closing curly brace. All of these things have purposes. Main is where the execution of the program is going to start. Those parentheses, that there's just an open and a closed one with nothing in between, there can be stuff in between. As it happens, nothing we're going to do in this class will ever involve the functionality that involves putting something in between there. But you could. And then curly braces. Curly braces are groups of commands. We'll see lots of it. I mean, we're going to be using curly braces all semester. Curly braces can be inside of other curly braces. They can be nested and so on. Right now, we are just looking at a curly brace that's going to contain the steps of the programs. This could, in fact, be... sorry here, I didn't realize I had these up here. So there's it's marked there that we have the parentheses, and then they have to have that matching set of curly braces. Anytime you have some kind of symbol in your C program that has a pair, like an open parentheses and a closed parentheses, you have to have pairs of them. Or a curly brace and a closing curly brace, or an angle bracket and another angle bracket, or a square bracket and a square bracket. They always have to match up. One of the really powerful, useful things that VI can do is help you match up your symbols. It can help you figure out, oh, I see, here's the problem, I'm missing a parenthesis. Or I'm missing a square brace, but we will learn more about that as we need to. So now, we learned that every C program has to have pound include math.h and pound include stdio.h. It has to have a main function, which is where the program will start. That will be step one of the program. Wherever main is, that's where it's going to start executing. That could be it. That would be the world's most boring program. That program doesn't do anything. But that would be a perfectly legitimate C program right there. But in general, where I have that red arrow on the screen right there, that's where you're going to want to start adding things. Steps, instructions, commands, whatever the right word you want to use is, as to what your C program is going to be doing. They go between those curly braces. So, clearly, one of the things any program we're going to write is going to need to be able to do is to write something onto the screen. How do you just get it to put text onto the screen? And the basic command that does that in C is printf. Printf is, strictly speaking, a function, and we're going to learn more about functions in a couple lectures, but printf is a function. And you can see here is an example of it where all my program is going to do is it's going to print the words, "This is the Weather Channel," for whatever reason, that's just what I put on my slides here. It's just going to print those words onto the screen. Okay? Printf is the command that does it. Notice it has to be one word. Let's look at the syntax here. Syntax, the ways in which the command has to be put together. Alright, we invoke the printing function using printf. C actually does not know what printf means, but stdio.h, those standard input and output headers, are something somebody wrote that teaches C how to write to the screen so that you can have this kind of basic input and output kind of thing. So that is what we're going to have here. We're going to have a printing function, printf. Alright? Every command in C ends with a semicolon. So that's part of how your eye can visually tell, you know, here's one command, then here's the next one, then here's the next one, is they have these semicolons. If you write a program and you don't have the semicolons where you need to, you're not going to be able to run the program. It's going to stop you when we compile the program. I know we haven't talked about what compiling means, but we'll get there. The business of the command of this function happens between these parentheses. Inside of there are the arguments that are like, what is this function going to do? It's exactly the same sort of thing as, like, imagine if you had sine of 2 pi. Okay, sine parentheses 2 pi. 2 pi is the information sine needs in order to give you an answer. In the same sort of way, the stuff between these parentheses is the information this function printf needs in order to do something, in this case, write it to the screen. So here we have this pair of parentheses. There's got to be a pair, an open one and a closing one, and inside of it is what's going to be happening. Okay, printf needs what should I be printing? So in this case, in the case of printf, the simplest way to use it is to just put the things you want to print in quotation marks between those parentheses. So like, I put quotation mark, this is the weather channel /n, we'll get there in just a second, is what the /n means, and then quotation mark. Notice, by the way, PowerPoint is rendering this where the quotation marks are angled. There's an open quotation mark and a closing quotation mark, and they're different symbols. Well, you don't have that on your keyboard, okay? That's just a PowerPoint thing. It recognized that they were matching. So, but you do need to use quotation marks. It can't be single ticks, it can't be back ticks, it has to be quotation marks. So in this case, the instructions that are going to the printf command, the printf function, is THIS space IS space THE space, this is the weather channel /n. We'll get again to what the /n means in just a second here. /n is the new line character. New line character means after the, so here it is on the screen, it's writing THIS space IS and all the way out through the weather channel, and then it says start a new line. So the next spot that will get used is on the next line of the screen at the beginning of, in the first column. It's like hitting on an old typewriter, hitting the, the return key, and the carriage slides back and the paper rolled up one. That's exactly what it's trying to do. So, in fact, that's literally exactly what it's trying to do, because old C computers they didn't have a screen. They were writing to a printer, with that long piece of paper in there, and the printer head would be printing the letter T, the letter H, the letter, and when it got to the end, the new line character, /n, meant roll the paper up one and slide the carriage back to the beginning of the line. Yes, it's really that old. All computer programming languages are rooted in very, very old technology. So, like, for example, I'm just giving you here a little piece of a program here. I mean, I'm not even giving you up in this here the pound includes and all that kind of stuff. I'm just saying main, open parentheses, close parentheses, and then between my pair of curly braces here that are grouping together the steps, I have a printf hello /n, followed by a semicolon, and then another printf statement that is got world /n, and then a semicolon, because you got to have those semicolons showing that that's the end of each of these statements, or these commands, or whatever. And then in that little blue box, I actually show you what this would look like, what it would run. It would write HELLO, and then it would hit that /n, which means new line, so it like rolls up one line, and moves down to the next line, and then back to the first column, and then it starts writing WORLD, and then it'll move on to the next line. Notice, by the way, sometimes this isn't immediately obvious to the students, notice that the commands happen in order. Okay? So, first, we're starting at main. There could be stuff up here above. There will, in fact, be in some of our programs stuff up above main, but we start at main. And the first thing that's going to happen in this case is we're going to print to the screen the word hello, followed by a /n. and then we're going to print to the world screen the word world, and then we hit the end of the program, and the program is done. And it'll return you back to your Linux command prompt, where you can do things like ls and so on, or log out, or whatever. Notice, by the way, we could have done other things here. If on that first line of the program there, where I had printf hello, if I just take out that /n and just replace it with a space, for example, look what actually happens here. It says printf hello space, okay, time for the next command, printf world, W-O-R-L-D, /n. Notice what happened. It wrote hello space W-O-R-L-D, just like I showed there in that blue box. It never got that /n. There was no /n in that first command that had the word hello in there, so it didn't move on to the next line. This can be a very powerful tool to build like a sentence on a screen if you need to put it together, but we'll see examples of that later. But you know, you can usually, most of the time in a C program, when you're printing something on the screen, then you put a /n to move on to the next line, but it might not always be. By the way, here's another example of a way you could use the /n new line character. Here in my little simple program here, I just said hello /n world /n, and what I printed was hello, and then it moved on to the next line, made a space, and said W-O-R-L-D. It may not be obvious that there's a little space there in that program. But yeah, these little simple programs, totally simple programs, they're not doing anything here. So, you know, here's another little sample one, okay? All this little program does, pound include the math libraries, actually no math is getting done here. We wouldn't have even needed to do that. Pound include the standard input-output libraries, well, we are using printf, which is in the standard input and output libraries, so we include them, and then we're going to use main, and we're going to just print hello world /n, and put a semicolon there, that we're ready for the next command, but there are no more commands. That would be the end of my little program there. Hooray! We could do this. We could make this work. That could be the end of our program. It's time to actually try to run the thing. What we have to do in order to run a program is we have to compile it. Here's the thing. Your C program is a set of letters and numbers and symbols like open brace and curly brace and so on. It's shocking, I know it, but you know what? Computers don't know that. Computers don't know any computer languages except one, machine language. Machine language is a complicated code of ones and zeros in lengthy strings that contain long sets of these ones and zeros that have very explicit commands as to what to do with this register in memory or what to do with these pixels on the screen or whatever. You and I and other people with actual human brains cannot comprehend machine language. Okay, I mean, don't get me wrong. Engineers at places like Intel developed machine language, but they can't sit there and type, alright, what do I want my program to do? 001, 0001, 000111. No, I mean, they developed this language, but we need something closer to the way our brains work, like C, in order to actually get our thoughts into a form that the computer can do something with. But the computer doesn't actually know C. Rather, the program has to be compiled into machine language. The word compile doesn't necessarily jive with your knowledge. A better word might be translated. Your program, your C program, needs to be translated into machine language so that the computer can do something like that. These programs that do this translation from a computer language that you and I can understand, like C, into machine language, which the computer can understand but we can't make heads or tails of, is called a compiler. A compiler is the piece of software that does this, and there's lots of these compilers. Anything from free that you can download off the internet to wildly expensive compilers that are, they have different pros and cons. Anyway, these compilers convert your program, which is in C, something your brain can function. You can think about what main means. You can think about what printf means. The computer has no idea what printf means. But the compiler converts things like printf into machine language, making the program quote-unquote executable. That means that it can run, it can be executed. Now, we have a compiler installed on our Linux computer here called GCC. It's the GNU it's the GNU Compile Cluster, I think is what it is. And it is a compiler that detects that this is a C program that it's trying to convert into machine language. And so from the command line, not inside VI, but from the command line, and I'm going to demonstrate all these in just a little bit, you do a GCC to invoke the C compiler, and then you tell it what program you're trying to compile, in this case test.c, and then a space, and then a -lm. What does that mean? That -lm is possibly our first example of a flag in this course. A flag is something like an adjective or an adverb to the commands that we are using in Linux, our operating system here. This -lm is modifying the GCC command. It's like an adverb that modifies a verb. GCC is a command, it's a verb, and it is being modified by lm. lm means link to the math libraries. To be honest, I've never really understood why that has to be done when you've already included the math libraries. I don't know. And then why don't you need to link to the standard I/O libraries? I don't know. I do know, though, that that's just the syntax of the command. GCC, test.c, or whatever your program is called, assignment1.c or whatever, -lm. Alright. So, by the way, you may, if you do some searching online or find a misprint in the book, it used to be the -lm went before the computer program's names, so if you come across a web page or something from the book that's more than maybe 10 years old, it's going to be saying GCC space -lm space in the name of your program. That doesn't work anymore. For some reason, that it's more efficient to do it the other way around. For some reason, I don't understand. GCC space the name of your program.c space -lm to compile the program. What the compiler will do is it'll take everything in your C program, which right now isn't much, but someday later will be a lot, and it translates that into a machine language that the computer's chip physically knows what to do with. The file that it creates has the incredibly unintuitive name of a.out. I once looked it up. I believe the A stands for assembled, which I don't really understand why. Assembled. But whatever. It's a.out. You're going to see that. You're going to type that word a.out 1,000 times this semester. A.out is the name of the file that the compiler has created. It took your program and it converted it into a file. It translated it, and the translation is called a.out. It's executable. That is something the computer knows how to do. If I go to the Unix command line prompt on my computer and I type /a.out, it will run. Now we have to have gotten that far. If there were errors in your program, it won't have compiled, and it'll have given you some messages on the screen like error line 23, you're missing a semicolon, or mismatched parentheses on line 47 or something like that. But if it didn't give you any messages, it created a new file called a.out, and you can run it using /a.out. I mean, just typing a.out almost works. The problem is there's thousands of different copies of this file a.out all over the computer from places where I've compiled programs, where other people using this computer have. You have to tell it you mean the version of a.out in the current directory, and remember, dot means the current directory. So // means in the current directory run a.out, and it'll do whatever your program just did. Now, before we move on to this next kind of little section here, let me give you some examples here. I'm just going to bust out of this here, and I'm going to go over here. I am logged into Chesapeake as my kind of dummy student account, student 315. I'm just logged in. This account has all the same settings your accounts do and so on. We're not doing anything fancy. And because my account, I have all kinds of weird settings and stuff like that going on that wouldn't be very representative of what your account is doing. So I made this dummy account. Alright, let's make ourselves a little program. I'm going to call it sample.c, just for lack of a better name. So vi sample.c, and in vi, I am going to go into insert mode, and I'm going to type #include math.h and #include stdio.h. I didn't actually put spaces between there. I think I will go back and do that just to be tidy about it. And my little program here says main, open curly brace, open parentheses, close parentheses, and close, then I have an open curly brace, and I'm following it by a close curly brace. That's a good habit, by the way. Don't think of a computer program as being something that you start at line 1 and you just type until you get done with it. Make pieces of it at a time. So like, if I put a curly brace here to start grouping some commands, go ahead right away and put the close curly brace at its end, and then other stuff is going to go in between. Now, what kind of stuff? Let's just do the same kind of silly thing that we did in the lecture just now, where what we might say, printf hello world /n. Alright, oops, got some typos there. Okay, printf hello world is the only command in that whole program right there. Alright, I think I don't even have any mistakes here, but we'll soon find out. I'm going to write and quit using the VI command. I pressed escape to get back to the command mode, and then :WQ to write and quit the file. If I do an ls, you can see, I forgot I have a whole bunch of stuff in this directory, but there is the sample.c program right there. Now, if I want to compile it, I type gcc sample.c -lm, and that is going to, oh, it doesn't look like anything happened when I pressed enter. Well, no, that's a good sign. That means it created the a.out file. In fact, if I do a list here, you can actually see, where did it go? Hey. Huh, wait a minute, I'm locked out. Hold on. What happened? Well, it's educational to see that things go wrong for anybody. I don't know if I just lost my network connection or what's going on here. There we go. For whatever reason, I logged out for a second there. Okay. You can see I actually now have a file called a.out. If I want to see that, you know, like, am I sure that's the right file? I could use like an ls -last. Remember, that tells us like all the details about the file. And ls -last, it tells us that a.out was created, this is July 16th at 12:31, which is exactly the current time. So there's my file. If I just want to run it, I can type /a.out, because it's in the current directory. I got copies of a.out all over the place on this computer in lots of different folders. I mean this one. And it just typed hello world. Let's actually go break this a little bit. I'm going to go ahead and VI back into my file here, vi sample.c. Let's try to break this here. What if I had forgotten the semicolon? Let me tell you, you're going to forget semicolons 1,000 times in this class. That's a useful thing to know. So let's just delete that semicolon, break back into command mode, :WQ to write and quit, and let's compile this thing. gcc sample.c -lm. And look what happens. You get some error. In function main, on line 9, error, expected semicolon before curly brace token. By the way, these little strange little A's with a hot check above them, or a hat, I think they're hats, not hot checks, but whatever. I think that is a font problem. Depending on your computer, what fonts you have installed and stuff like that, I think those are supposed to be a kind of a fancier quotation mark that I just don't have the right fonts installed on my computer. So it might work on yours. It isn't working very well on mine, so it looks kind of ugly. But in function main, error, expected semicolon before the token or symbol, curly brace. Well, let's go back in. Hey, by the way, notice I'm using my little shortcut here. Bang V, !V means do the last command that started with V. Well, the last thing I did that started with V was vi sample.c. It saves me several taps of my fingers, right? So it says, oh, line 9 was the problem. Remember, here's a good example of why VI rocks. I can go type, while in command mode, I'm not sure if I'm in command mode, then go ahead and hit escape. Now I definitely am in command mode. 9, capital G, takes me to line 9, which is the curly brace at the end here. And it said it expected a semicolon before that. Oh yeah, because right here, there wasn't supposed to be a semicolon. Okay? So now my program would work. Heck, let's demonstrate that to ourselves. Heck, I'll even save myself a few more strokes on that keyboard by typing bang G for do the last command that started with G again, which happens to be gcc sample -lm. And if I run it, it works. Alright? We can break this in other ways as well, or make it work. What if I had forgotten the F? That's something I type 100 times a day wrong, as I type print instead of printf. What happens then? Alright, I get back out of VI, and I'm going to try to compile this thing with the bang G command. In function main, sample.c, undefined reference to print. Okay, the rest of these errors don't necessarily, and this is some detailed stuff here. Oh yeah, it says print. I don't know what print is. I only know what printf means. There is no command print in C. There is no command print in stdio.h. If I fix that, it will work again. Alright, let me give you a couple more things here that we could do. I'm going to add another command. This is going to be a really long line because it contains my list to Santa. it contains, oh, I'm running to the ends of the line here. It contains my, what am I going to do when I get to the end of the line here? My list for Santa. I just sort of went right over the edge of the line. Went right off the top end of the window and came out the other side. By default, well, that's not a good way to put it. This is bad style, okay? You don't, in general, want your lines to wrap past the end of the screen or whatever. This would work, but it gets to be kind of messy. It's much, much better if, once you get close to the edge of a line, go ahead and, like slash N, and move on to the next line, and just continue it down here, okay? In general, that's how you're going to want these things to work. The way I had it before, it would run, but it would be messy. And this is going to look much better. Here, if I compile this thing and run it. This is going to be a really long line because it contains my list for Santa. And see how after the word it put a slash N, a new line character, or scroll down one line farther, and then type the rest of the line about contains my list for Santa. But, we wouldn't have had to. Let me go ahead and demonstrate what happens here. If let's use a powerful VI command here. You don't necessarily know this one, but big J is join two lines. So I can pull up the previous line up there. I mean, this is ugly, how this line wraps around over here like this, but in fact it would work. Okay? But it's a poor programming style. So in general, once you get to the end of a line on the screen, you want to go ahead and move on to the next line in the command like that, in the program like that. It just looks better. Notice, by the way, that we are indenting as we go along. So, like, all of these commands are at the same level, like on an outline. There will eventually be further indented things. By the way, notice if we try to put something outside of this main function, outside of those curly braces, I'll just put the word outside right here, right now, just to show you what's going to happen. So, what will it do here? We have part of this program outside of main. If I try to compile it, error, expected declaration specifiers or ... before string constant. I don't even know what most of that means. What I know that means is I'm outside of the program. Okay, once I'm outside of the program here, that didn't work. Everything that your program is doing is going to start here at the word main and work its way down. There can be and will be other stuff up here at different times in our program, but that is not what we're doing right now. Okay. We're going to learn next about variables in C, and we'll then start learning about how you print, like, you can have a variable with a name like temperature, and then you can put values in it, or do math, make calculations with that, and then you can print them. But we'll get there.